So last new thing is Snell's law. Snell's law is really the application of what happens when light travels from one transparent medium into another. Okay, so we have water and air. So we're going to go have a light ray that travels from air into water. And it will refract or bend. I have an example of this sitting on my desk, a pencil sitting in a glass of water. Now, how many transparent media are there between the pencil and your retina?
Two. Actually, water, glass, air. There's a the fluid in your eye.
Yeah.
I remember this.
You're right.
Then there's the vitreal fluid.
We're up to 5 now. We got some vitreal fluid in there. You got 5?
My glasses.
Your glasses, you get more. That's right. All right, let's count. You want to count for me, Andrew? You got your fingers up? So let's start with water, and then glass, air.
Vitreal fluid.
Hold on. Now the light hits your cornea. Is that a surface?
Yeah.
Yep, so we're up to 4. You don't have to draw that. We already have that. And then after the cornea, there's some vitreal fluid right here. So now what are we up to? 5. And then lens, and then vitreal fluid again, and then we hit the retina. And if you're Stephen, you have glasses. And then a kid, second hour said, does glass count as 2 surfaces? Because technically you've got like the inside of the glass and the outside of it. So there's a bunch of bending going on here, right? Is the point. Not only that, but the light is bending, but also because it's sitting in a circular beaker, it's also acting like a lens. So it's not just bending, but it's also bending and being sort of oriented differently. So it changes the way that pencil looks, right? It will both magnify it and make it appear like it's bent and also kind of shift it over. That's that combination of the fact that it's a lens and different media. All right, so what does this mean for us? When light travels from one transparent medium into another, and we're going to not worry about what happens between the cornea and the retina, because every time we look at an object, the light bends as it goes through your cornea, your vitreal fluid, your lens, your vitreal fluid, and your retina again, right? That happens every single time. So we're just worried about the stuff outside the cornea. Light will bend because it changes its speed ever so slightly. Now, it's not a big difference, but if I'm a photon of light, it is. So in other words, if I took a laser and somehow magically you guys could have quick enough reaction time, so if I turned on the laser, shone it across the room, and we could time, right, the amount of time that it takes a photon of light to go from the laser to the other side of the room, and then divide by the, so distance divided by the, we could figure out how fast.
Speed of light?
Yes. And then if I did that again, but I were to shine the laser through like a fish tank, it would slow down just a teeny bit. Not enough for us to notice with our like reaction time, right? Because it's still really, really fast. But if we compare the two, we get something called the index of refraction. And the index of refraction is a little bit like mu. It's a ratio between the speed of light in the vacuum of space divided by speed of light in whatever transparent medium we happen to be measuring. Okay? And so let me give you an example. Let's find the n value for water. So light will travel through water. The speed of light in the vacuum of space is 3 times 10 to the 8th meters per second. The speed of light in fresh water is about 2.26 times 10 to the 8th. Yeah, now, if I'm a photon of light, that's a big difference. If I'm measuring the speed of the laser beam through the room as compared to through a fish tank, ain't going to notice, because the important part of this is the order of magnitude, right? It's the 10 to the 8th part that's important. That's the super, super fast stuff. This is just like confidence limits. This is not very much. But watch what happens when I divide. First of all, there's no units, just like in mu. It's a ratio. And secondly, that part of the scientific notation also cancels. So I end up getting 3 divided by 2.26. Now that's something that's noticeable. And indeed, the N value for water is 1.33. N is always greater than 1. N for air, by the way, speed of light in a vacuum divided by speed of light in air, turns out to be 1.0003. So what does that tell you about when light travels through air as compared to the vacuum of space? Right. Not much of a difference, right? Just a little bit. So we assume air's index is just 1. So it slows down enough when it goes into water that it's actually noticeable. And you can see it, right, in the pencil. It looks bent, it looks magnified, it looks kind of shifted over. So that's the effect. The biggest index for a natural substance is diamonds. So diamonds are pretty optically slow for light. They bend light a lot. And in fact, they bend light so much that the light actually, especially when you cut the diamond in a shape where it has lots of different angled surfaces, yes, the diamond will trap the light, it'll bounce around for a while, and then it'll escape, and the effect of that is, ooh, sparkly, pretty colors.
Disco.
Okay?
Isn't there something like that they can do with Jello? If you shine a laser through Jello, it'll bounce around inside the Jello?
You see this?
Yeah. What you must do for fun, Stephen.
I can do that, right?
All right. So we always measure, by the way, for Snell's law, we always measure the angles to the normal. And so there must be some math that we can do here. And there is. I am not going to actually derive the equation for you. However, if you were to look at light that goes from air into water, we got some parallel light rays here, and they bend, right? You can create two right triangles. And so with these two right triangles, they have a common hypotenuse, right? Hypotenuse for this guy. They're not the same right triangles, but they do have the same hypotenuse. Those two right triangles have a relationship, and if you want to, for extra credit, you can look up that relationship online. I know you can all follow it. It's just not particularly meaningful. So when I've gone through the derivation, usually in an honors class, the kids are very polite. They copy everything down, and by the time I'm all done with a page full of derivation, I've got like two kids that are like, well, that was fascinating. The rest of you are like, well, so I'm going to just show you the finish line. Here is the finish line. Snell's law says N1 times the sine of theta 1 is equal to N2 times the sine of theta 2. So the N value for air, let's say we're doing air versus water again. The N value for air is 1. So if I did 1 times the sine of this angle, it would be equal to the N value for water, which is 1.33, we figured out down here. So 1 times the sine of this entering angle would equal 1.33 times the sine of the exiting angle. It's a very easy math problem for you guys. It'll just be, I give you 3 of the 4 variables and you solve for the unknown. Okay? No units for N, and the angles are in degrees. So your homework tonight, 15A, 1 and 3, is just practicing a couple of those Snell's law problems. Now, another thing I might do is ask you, can you tell the fast or medium just based on the way the light bends? And the answer is yes. Let me show you. And these, you want these are easy. So let's say I have air and water, okay? Air is faster than water, and the way light behaves is whenever it goes from a faster medium into a slower medium, it bends toward the normal. So it makes a more acute angle with the normal in the slower medium, okay? So a way to remember that is there's a little bit of alliteration. Slower equals smaller angle. Big equals faster, which that makes sense too, right? Big guys run fast if they're in shape, I guess. All right. Not always, yes. Yeah, if big guys run fast, that's serious.
Eric could beat Wesley.
That's why, and then we're back to facial recognition, right? See how I brought that back home? Big, fast, facial recognition. Okay. So here's what you might see on the test. Medium A, medium B. Which one's faster?
B.
B's faster. B's faster. But I might, you never know, I might do something crazy like this. Oh, look, it's askew. Which one's faster? Okay?
Wait.
All right. Easy peasy, right?
But in the glass, bending away from the normal.
Remember, there's a whole bunch of stuff happening there, so it's not quite that simple. That's mainly because of the curvature. Is that better? Yeah. Okay. All right, there's one last thing. One special exception or special example of Snell's law, special condition. So let's say that I have a light source underwater. Oh, it's like a flashlight. Flashlight underwater. Okay? And I have a light ray that shines from water into air. Which way will the light ray bend? So let's say that this is, it's like its original orientation. Will it bend toward the water surface or toward the normal if it goes from slow to fast? Right, toward the water. Good job. Nice job, guys. Okay? So that is correct. Now let's say I have another light ray from my flashlight because it makes a beam that's pretty wide, so a lot of different angles. Say I've got another one that makes an even more obtuse angle between the water and the air, so an even bigger angle. So then what will the exiting light do? Go even more close, right, closer to the surface of the water. That's correct. So wow, even more obtuse angle right here. And there would be some point at which the entering light makes such an extreme angle with the normal that the light can no longer escape and it just skims the surface. It actually will ride sort of parallel to the two surfaces. That's a special case, and it's called critical angle, theta critical. And so the exiting light will be at a 90-degree angle. Who knows what the sine of 90 is? Because, you know, if we go back to Snell's law, hey, we got some stuff there. What's the sine of 90? I think it's 1. 1, yeah. But you had the right idea. It's something not normal. And then if you go beyond critical angle, so like even more obtuse.
Isn't that where if you're underwater and there's that reflection from the ground?
Nobody else knows what Stephen's talking about? Yeah, swimmers probably have done this before. This, by the way, has a special name too. It's called total internal reflection, and I'm going to show you some examples of this tomorrow. Total internal reflection. One of the cool things about teaching as long as I have is that when I first started teaching, this was just cool. Now we have a real life application for this that everybody here has seen or used at some point. So we'll talk about that tomorrow. But if you're a swimmer, you've noticed this. Let's say that you're sitting in a pool underwater. You're sitting underwater and you're looking around, and if you look up, like right above your head, then you're in this neighborhood, and you can see, like, oh, there's my friend sitting on the pool deck. Oh, hello, I can see. If I'm in, like, Lake Michigan, ooh, seagulls, you can see everything above you. But if you look at a more obtuse angle, you're going to get this effect, and actually it'll be like this back to your eye, so this is you now. And it'll look like a mirror.
Wait, so can you explain to me internal reflection, or are you doing it right now?
I will give you more examples tomorrow. Total internal reflection means the light basically stays trapped. It doesn't exit. So the water kind of acts like a mirror here. Okay? It's a really cool effect. It kind of looks like liquid mercury or like stuff that the Terminator 2 and more are made out of, right? Anybody with me?
Yeah.
Anybody?
You bust the cabinet kid, he's like, all the way back, oh my God.
Yeah, that guy.